So if I was to just kind of write this out, a vector product will have one vector times another vector and will equal the product. So I used torque as my example for reminding you about the right-hand rule. The equation for torque is R, the torque arm, and I put the vector bar on top of it to remind us that the torque arm is just a displacement vector, but it has direction, cross the applied force, and that equaled the torque, and we use the lowercase tau for that. That's what you should have learned last year. The cross product has a magnitude, the size of this answer, which was just the size of the vector, the torque arm, the size of the force, and the size of the angle between them. And that would give you the magnitude of the torque, the number part. But the right-hand rule is what gave you the direction. Now, by definition, and just look at your hands, the direction of the product is always perpendicular to the plane created by the other two vectors. Geometry honors told you that two rays define a plane. Remember geometry honors? As long as those two rays weren't collinear, any two rays can define a plane. If you don't like that, you can say two lines define a plane. You guys do remember that, right? Boy, I'm getting a lot less confident faces now. But any two lines can define a plane unless the two lines are collinear. Right? So that's true here too. We get a resultant product as long as the two rays are not collinear. If the rays are if the rays are collinear, this angle is either 0 or 180 degrees. That produces no torque. That's like me coming over to the door and pulling on the door handle this way. Will the door open? Sure as hell won't. Or if I come over here and push towards this, or even down, it's not going to work. Because I have no component of the force that is perpendicular to the torque arm. So the mathematics agrees, but there's a geometric part here. So I am going to say this. Pointer, middle, thumb. The first one is the pointer finger, the second one is the middle finger, and the result is the thumb. Now, if you will recall, with electric fields, force equaled charge times the electric field. It was really easy. The direction of the force was in the direction of the electric field, unless the charge was negative, and then the direction of the force was in the opposite direction of the electric field. Simple enough. Magnetic fields don't play like that. See, magnetic fields are weird. They are dynamic. Except I can't spell dynamic right, so you should really find yourself a better teacher. There, dynamic. Magnetic fields are dynamic. If you have a charged particle in a region of space with a magnetic field, oh, you're going to love this. What letter do you think we use for a magnetic field? M would be nice, right? Yeah, B. Uppercase B is the letter assigned for a magnetic field. In fact, it would not be uncommon to hear somebody say, what is the direction of the B field? And they're saying magnetic field. I would love to tell you why it's the capital B. I have no clue. I've never bothered to look it up. I stopped worrying about that when P stood for momentum. I'm like, well, we're done now. It doesn't make any sense. I don't care. So B, yes, capital B is the symbol for a magnetic field. Magnetic field is a vector quantity, like an electric field would be a vector quantity. And it is possible to create a uniform magnetic field. Well, I will show you how in a couple of weeks. But right now, we'll just have to assume that these magnetic fields exist. right now, the force on this charged particle is 0. It's in a magnetic field, but the force on that charged particle is 0 because the magnetic force is much different than the electric force. So I'm going to put a little E here to tell me that that would be the size of the force from an electric field. The size of the force from a magnetic field requires something that isn't present yet. You see, it's dynamic. The charge has to be moving to experience a force from the magnetic field. Stationary charges don't experience a force from the magnetic field. But in order for there to be a force on a charged particle from a magnetic field, the particle has to have some velocity. Now, it's a little weird, but I want you to think about what this is kind of entailing too. This means a magnetic field can't be used to start a charge into motion. If the charge isn't already moving, there's no magnetic field that will get it moving. You guys understand what I'm saying? I'd get that in there in big letters because I'm thinking your multiple choice is going to have some weird options, right? You can see how this is going to be one of them, but this is an absolute. A magnetic field cannot start a free charge into motion. Every one of those words is important. That's why those multiple choices that get you, a magnetic field cannot start a free charge into motion. Now, if that charge has a velocity, well, now we're talking. All right, now we can do something with that. In fact, here we go. I think we should figure out what is the direction of the force on this charged particle under this circumstance. So let's apply our right-hand rule, right? Start this way, and I would encourage you to pay very close attention here because we're going to go this over and over again, and then we're going to have like pop quizzes to make sure you get this perfect. This is on the exam every time, and I want you to get this one because if you can't get this, we can't get the next part. So you start. Get your little thingy out here. Make sure it's the one that doesn't make the L, okay? You're going to do it, and I'm going to make fun of you because you're going to be holding your pencil in your right hand, and you're going to do this, and you're going to screw it up, okay? Start by pointing your pointer finger in the direction of the velocity. And then rotate your middle finger until it's pointed in the direction of the magnetic field. Now, in the future, keep in mind, your piece of paper in front of you can be moved on your desk to make this easier for you. Because I can contort you in all sorts of ways to get you to do stuff, and is so much fun for me. So, this suggests that this object experiences a force, but the force is perpendicular to the plane of the board, right? It's into the board. You guys see that, right? Which means we're going to have to come up with a way of describing and illustrating a vector that is into or out of the board. And we've already defined this before, but it might have been a while. I'll remind you that a dot with a circle around it is used to describe a vector that is out of the board, and a cross with a circle around it is used to describe a vector that is into the board. The idea here is silly, but it kind of makes sense. If you imagine somebody has an arrow and they fire an arrow. If the arrow's coming towards you, you would see the point of the arrow, right? If the arrow's going away from you, you would see the fletching of the arrow, the feathers. So that's kind of why we do that. And so what I would have you do here is say, okay, the force is into the board at this point. Good so far? Want to try again?
Yes.
Oh yeah. We're in every possible permutation of this. So I'm going to keep it relatively straightforward if I can. Let's do one of my favorites. Let's do a magnetic field that is upwards. All right, so upwards magnetic field, and our particle has a velocity that is this way. All right? We want to find the direction of the magnetic field. I'm sorry, the force on the particle from the magnetic field. So, but if I want to say that a magnetic field fills a region of space, but that the magnetic field is into the board or into the paper, a field of x's is used. Generally, you don't put a circle around each one because it becomes too cumbersome, but the field of x's suggests a field that is into the board. Everybody okay with that? So this is a magnetic field that is into the board. A field of x's like that. And let's say my charged particle has a velocity that is downwards. So right-hand rule would say the force will be this way. Nope. This way. There we go. Now, it's right around this moment that I have to decide whether we need more practice or not. And I always think we've had enough, and I'm always wrong. So let's do another one, shall we? So, how about we do charged particle has a velocity that is into the board, and there is a magnetic field that is pointed upwards. Okay, so the velocity of the charged particle, and I know I've got a dot and a cross. I'm trying to represent that the particle has size, but I'm saying that the velocity is into the board. Uh-oh, Sergio's got a... How about this one? I'll leave the magnetic field pointing upwards. And my charged particle is also has a velocity upwards, in which the force on the particle would be 0. There is no plane defined by the direction of the velocity and the direction of the magnetic field. So that gives us a force of 0. Again, the angle is 0 degrees between the velocity and the magnetic field. Opposite direction would have the same effect. So if I have another same particle over here that has a velocity downwards, it also would experience a force of 0. All right? How much time do I have? Less than a minute. All right, so remember the size of the force. But it's in order. This product is in an appropriate order. All right, so we figured out that the force is going to be this direction. Let's look at a few pieces that I didn't discuss yesterday, but are we all okay with that? That part's pretty straightforward. We've got the right-hand rule down here. So just remember, this order will be the same every time. We could have written this in any order. You think multiplication occurs in any order. It does not occur in any order. Does everybody understand? When it comes to vector multiplication, the order matters. Who knows matrix math? Anybody? 2 of you. Things you guys don't know. The dot product and the cross product can be done through matrices. And if you are aware of how the determinants of a matrix operates, you can figure out what the cross product and the dot products are by expressing your vector as a matrix. A vector is a 3x1 matrix, or 1x3 matrix, depending on how you want to do it, right? X, Y, Z, that could be your matrix. If you make a 3x3 matrix, with the top one being, God, let's knock it off. Top one being IJK, and then put in your vector here for V and your vector here for B, then you can do matrix manipulation to figure out the resultant of the cross product and dot product directly from a matrix. This is how it can be done in a calculator or a computer. They used to make matrix calculators where you could type in your matrix and it would operate on the matrix in your calculator. They haven't for a long time. The last company that was making a matrix style calculator was HP, but it's been off the market for years. I think TI and Casio has largely taken over, but matrices is a much faster way generally to do a lot of mathematical operations. Let's talk real briefly about the units here. If we assume that the sign doesn't have a unit, then the result of finding the magnitude of this force would yield just QVB. If we solve this for B, then we get force divided by charge and velocity, which means Newton divided by Coulomb meter per second. That's the unit for the magnetic field. Now you, of course, can plug in stuff here and reduce this a little bit by putting in what we know for a Newton, but ultimately the Newton over Coulomb meter per second has a name, and it's called the Tesla, in honor of Nikola Tesla. So we measure magnetic fields in terms of Tesla. A Tesla is a large value for a magnetic field. So a 1 Tesla field would be a very large field. Most of the time, we measure, the fields that we measure are in what's known as Gauss. And I believe it's 10 to the 4th Gauss is 1 Tesla. I believe. I don't use Gauss very often. But has anybody heard the phrase Gauss before? All right. So your little magnets and stuff that you stick on, they're just a couple of Gauss. They're pretty small. One of the labs we're going to do next week, if I can get it to work, is to measure the strength of the magnetic field of the Earth. It's powerful enough here, at the equator, near the equator, where we can get a pretty good measurement. It's not easy. It's not easy to do the lab. This isn't going to show up that often where you'd have to know what a Tesla is, but you probably should work on getting it to memory somewhere. So the biggest magnetic field I've ever operated with. All right, so enough of that. I want to focus on this diagram for a minute. If the particle experiences a force that is perpendicular to the velocity, one of the first things I want you to get into your notes is we said earlier that this force could not start the particle into motion. The particle had to already have a velocity to be moving. But this force is perpendicular to the velocity, which means the work done by the force also is 0. The magnetic force can't do work on a charged particle moving through the magnetic field because the force is perpendicular to the direction of motion. Therefore, the dot product for work, which is, force dot displacement, that works out to be 0 every time. So although this force can change the direction of the particle, it's not going to be able to do work, which means it can't change the kinetic energy of the particle. That's another thing to know. It can't change the kinetic energy of a free particle. If no work is being done, then there can't be a change in kinetic energy. Now, what can happen is that particle is going to start traversing a path that is curved. Right? You can see that right away because the force is perpendicular to the direction of the velocity, which means that after a moment passing through the field, the velocity is going to have changed directions. Now, using your right-hand rule, can you figure out the direction of the force now? Because the velocity's direction has changed. I need you to convince yourself that if the direction of the velocity has changed, the direction of the force has also changed. So the velocity is this way. Out of the board suggests that we're going to have a force that's still directed perpendicular to the velocity. And this has to be true. The magnetic force will always be perpendicular to the plane created by the velocity and the magnetic field, which means by definition, and if you didn't want to write that whole big sentence down and you didn't write it down yesterday, you should have written it down yesterday. So I'll say it slowly again. The force has to be perpendicular to the plane created by the velocity and the magnetic field. Well, that means that the force will always be perpendicular to the velocity. It will always be perpendicular to the velocity. This is why a particle moving through a magnetic field will almost immediately begin moving in uniform circular motion. Okay? A free particle traveling through a magnetic field will almost immediately begin moving in uniform circular motion. It's going to experience a force that is always perpendicular to the velocity, and that force will only cause it to change direction. As long as the velocity stays the same, the force will stay the same. And as long as the force stays the same, we will have the conditions for net force equals MAC. Now look, folks, you're going to have to dip back into your first semester physics from mechanics or AP Physics 1. So let's do a quick reminder of some stuff you're supposed to remember from way back when. If you have an unbalanced force that doesn't have a component in the direction of motion, then that unbalanced force causes a change in direction. That requires that we consider that the acceleration isn't about a change in the speed. So this particular acceleration isn't going to be v minus v naught over t. Do you remember what this acceleration is for something traveling in centripetal motion? Close. V squared over radius, yeah. This is how you calculate the centripetal acceleration. Remember, the velocity is not going to change, so that value stays constant. This produces the radius of curvature. There's another way to calculate it, and it's something that's worth looking at. If you were successful during your time in rotational motion last year, you'll remember that there's a relationship between the tangential velocity and the angular velocity for an object. If you don't remember it, I'm willing to provide it for you. That the tangential velocity and the angular velocity are related. So you can write the centripetal acceleration in terms of the angular speed as well. Now, there's a few other things that I want you to remember from first semester physics. So as I bring all these to bear, should I do some example reminders of what this might look like in a problem? Or should I just word vomit all the other things you need to know that were part of first semester or part of mechanics or AP1? All right, let's take a look at a quick example of what you might be forced to do here is to do this problem right here. Everything you need. Just relate the variables. A problem that's known as a mass spectrometer problem. And this is a pretty common problem on the AP exam, but it's also just a pretty common physics question. The idea of a mass spectrometer looks something like this. You have a region of space where there exists a magnetic field that is uniform. Outside this region of space, we have an area that is shielded and we fire a group of particles into the room with value q. So generally, maybe you have a particle accelerator outside this room. Perhaps you have set up an area of space where you know that there is a nuclear reaction taking place and you're collecting a range of particles. You could use the magnetic field to help sort the particles and help you determine what they are. So consider these particles enter the chamber with their tangential velocity. Describe the path that they will go on. This isn't an accidental path. this will have to be very pertinent. So what would that path look like? If we assume that they are positively charged, what direction do they go? They'll immediately experience an upward force, but of course their path is going to curve. The path isn't arbitrary. The path has to be a perfect semicircle. Well, that's not perfect. Let's do better. Right? It has to be semicircular. So they will strike the wall over here someplace, and they will have performed a perfect semicircle and hit the wall 2 radii away from where they entered. Now, can you relate the variables together that would tell you where they're going to strike the wall using Newton's second law and what you just learned about forces on moving charged particles? If your answer is no, I will be sad and I will get over it. But if the answer is yes, just put together what we did. Start with net force equals MAC. And start doing some substitution. I've given you all the substitution. Last year, I just assumed students would put stuff together, and I assumed wrong. So can we agree there's only one force being experienced by the charged particle when it enters the chamber? So the value of that will be QVB times the sine of the angle, which in this case has been established to be 90 degrees relative to the field. That has to equal M, and you did either V squared over R or omega squared over R, but I think for this one, V squared over R makes appropriate sense since we were given the velocity of the particle. Now, yes, we've related the variables together, but do you notice that one of the V's cancels out? So QB equals MV over R. So there's some obvious things here, but do you see now that you could do a whole number of things here? Like, the reason I call this a mass spectrometer is if all the particles are entering this chamber at the same velocity, then they will be separated by mass, with larger particles having a larger radius. Right? This side's going to be the same. So you would separate out the particles based on their mass. That's one thing that can be done here. And this is one way that a mass spectrometer can work. So I know you guys who have had AP chemistry have probably heard about mass spectrometers or devices that can be used to determine the mass of different constituent components. This is one way to devise one. It's not a particularly good one because it has to assume that the velocity of the particles entering the chamber have all the same velocity. But there's a way to select particles to have the same velocity. In fact, I'm going to show you that in just a minute. But this is one of those kinds of problems that involves net force, centripetal motion, and now this added idea of force on a charged particle from a magnetic field. So you can see any number of things, like what size magnetic field would cause the particles to curve under a certain radius. Do you guys see those kinds of questions now? So all I meant by just relating to variables is understanding that this is a pretty straightforward net force problem. It creeps into the exam from time to time. It's not particularly interesting. There are more interesting things we can talk about. Good so far? All right. I've never seen the Northern Lights. Has anybody in the room seen the Northern Lights? It is a thing I would like to do. So those particles from the solar wind get trapped in the magnetic field of the Earth, and they spin faster and faster as they get towards the poles. They generally get closer and closer to the atmosphere as that happens and start scraping the top of the atmosphere. The aurora borealis is a combination of 3 or 4 different effects. One of them is the heating of the upper atmosphere due to these particles scraping across the top. But these are also ionic particles, and they are charged. So their angular speed in that circle can be fast enough to produce an electromagnetic wave that we perceive as light. So if you've ever seen video of the aurora borealis, what you tend to see is a flashing like sheet as those particles are streaming across the sky. It's actually those particles scraping across the atmosphere as they get closer and closer to the poles. And it surges because generally it's based on an influx of charged particles. We're having charged particles hit the atmosphere all the time, but you get a surge from solar activity that brings a lot more particles all at once. So the particles are always doing it, but during a surge, so many more are doing this that you can then begin to see them in the atmosphere. So that's what an aurora borealis is. And that's why generally it can only be seen near the poles. And although we tend to associate it with winter, it's more associated with the fact that it's generally cold at the poles all the time. So you can have an aurora borealis at any time, but it's connected to solar activity. So we're in a more active cycle of the sun right now. So that's why there's been more active aurora borealis. The aurora borealis is cyclical. So it occurs at the same kind of cycle that our solar cycle occurs at. But again, it goes right back to this uniform circular motion effect that occurs with particles that strike a magnetic field. Okay. Enough for the basics. One more thing about free particles in a magnetic field. And after this, we're going to switch gears a little bit. A moment ago, I said that you could use this to select for velocity. I want to talk about that for just a moment. I want you to imagine I have a region of space where there is a magnetic field pointing out of the board. And I have electrons that have velocities like this. Now, actually, let me make this simpler. Let's assume for the time being that the electrons have just a straight velocity into the area of the magnetic field. What will be the direction of the force they experience as they pass through the magnetic field? We all do this and this, so it's down, right? Electrons are negative. Sorry, dude. Right? So we need to start being aware of that. It's a simple way to catch you, and you see how I caught you pretty quick? Well, at least one person. So the actual force that will be on this electron will be downwards, because we're dealing with electrons. So it experiences a downward force due to the activity of the magnetic field. So I want the particle to not drift downwards. So I want to add a field that will prevent the particle from drifting downwards. I want to add an electric field. What direction would the electric field have to be in order for the electron to not be pushed downwards? Think about it for just a minute. Be careful. Think about the idea that the force on the charged particle is not going to be in the direction of the electric field, but is going to oppose the direction of the field because the charged particle is negative. So either point up or point down, because you know it's got to be one of those, one or the other. Well, if we vote by democracy, downward would be the direction you all think it's going to be. Does that make reasonable sense? Will this produce an upward force on the electron? It's going to be an upward force on the electron. The electron is going to be pushed in the opposite direction of the electric field. So there will be a downward force due to the magnetic field and an upward force due to the electric field. If I want the particle to pass through this area undeflected, I want the net force on the particle to be 0. There are two forces acting on the particle. There's the force in the electric field, which is upwards. We'll make that positive. E times big E. And there's the force. Do you have a question?
So are magnetic fields charged?
No, magnetic fields affect charged particles.
So why does it make the electron move the opposite direction?
Electron, it does not make the electric.
Why would the force on the electron be the opposite direction if it's an electron and not another positively charged?
Well, the electron is negatively charged. So its behavior, any negative particle will do the opposite of what a positive particle will do. So if a positive particle experiences a force in one direction due to a field, the negative particle will experience the force in the opposite direction. Does that make sense? And that's true for electric fields and magnetic fields. So that's why. So that minus QVB, not Q, EVB, has to equal 0. Now, this is pretty quick, but obviously I hope you see that there is a specific ratio of the size of an electric field and the size of a magnetic field that could select for velocity. Meaning, if the particle has a different velocity, if it's going too fast, it'll curve one way. If it's going too slow, it'll curve another way. But if the particle's going just right, then it'll pass through this area at the same velocity. All the particles will have the same velocity. We've talked a little bit about this, but if you're trying to create a particle gun, and particle guns are used all the time for lots of different things, one of the things that you generally want from your particle gun is consistency. You want the particles to all have the same velocity, be in the same direction, be collimated. That way you can use them to do stuff. So a particle accelerator generally has a magnetic field and electric field being used at the same time to guarantee that the particles that make it out of your particle accelerator all have the same velocity. And there's other things that you would also try and do. Maybe you want them all to have same charge, same velocity, same mass. So we can do other things here to select for all of those things. I will point out that the charge didn't matter, did it? All particles coming into this chamber, regardless of their charge, positive or negative, are selected for velocity and nothing more. So anything that has a different velocity doesn't make it through the chamber without hitting the walls. Everything with the correct velocity can pass through the chamber undisturbed. Does that make sense? It's called a velocity selector. Now, building a particle gun sounds really exciting. It's not nearly as exciting as it sounds. In order to build a particle gun, you have to build it in a vacuum, because you try and build it in the air, your particles keep hitting other particles because there's air there. So they're not particularly exciting unless you can somehow draw a vacuum. Most particle guns or particle accelerators are built inside some kind of cathode ray tube. And the tubes that are in televisions, they have particle accelerators inside them because the tube is a vacuum. Does that make sense? Not just an inert gas. It has to be a vacuum. Otherwise, your particles keep hitting other particles. Particles or negative particles. So the effect is called the Hall effect. And it's such a simple and elegant experiment. I've got the stuff to try and do it. I've never gotten it to work outside of college, but I've got the stuff to try. So maybe we'll try and see if we can do the Hall effect experiment. I've also ordered some apparatus that might work, but right now I got told that it was, for the Hall effect to work, we need a couple things. First, we need a circuit, but we need a circuit, and then we need a place in the circuit where I can have a conductive sheet, something that's wide. So these wires can be any kind of connecting wires. They don't have to be special, but I need to have at least some place where maybe I use like aluminum foil or something I can cut into a very thin strip, a thin sheet, but is also conducting. Now, we've had conversations about this, but one of the conversations we've talked about is that we've done electronics from the standpoint that it is the flow of positive particles that are passing through the wires. So if we continue that idea, that these are positive particles passing through the wire, then in this piece of metal, there'll be positive particles passing this direction through my sheet, correct? If I apply a magnetic field to this sheet, I should be able to cause those particles to drift to one side. So let's place a magnetic field this way along the sheet. Now, again, we are assuming that we have positive particles passing through the wire. If we make that assumption, using your right-hand rule, what direction will these particles drift? guys? So I think they're gonna drift to this side of the sheet. So they will all begin to pile up over here. They're still gonna be generally tracking downwards, but we should have a higher concentration of positive particles on this side of the sheet. If that is true, then we should have a potential difference that is positive in this direction, because there'll be more positive particles there. That should create a potential difference across the sheet. Does that make sense? So if I just place a voltmeter, maybe not at the very edge there, that's probably the wrong place to place the voltmeter. If I was actually building the lab, I'd probably put the voltmeter in the middle of the sheet right here. And measure the voltage, I should see a high potential here and a low potential there. Now, this can only help us if when the negative charges do this, they don't do the same thing. So we expect the right side of this sheet to be positive if it's positive charge carriers moving through the wire. Does that make sense so far? Let's consider what would happen if it were negative charge carriers moving through the wire. Same magnetic field. So the magnetic field is going to be still into the board. But remember, if it's negative charges, then the negative charges are entering at the bottom because they travel in the opposite direction. So what direction will the negative charges be pushed when they enter this region of space with the magnetic field? So is this our right-hand rule for this relationship? Pointer finger upwards, middle finger into the board, thumb pointing to the left. But these are negative charges, so they're going to be pushed to the right. If it's negative charge carriers, then we're going to expect the electrons to pile up on the same side that the positive charges would have piled up on. But that would flip this potential. With a simple sheet of aluminum foil, a magnetic field, and a voltmeter, we should be able to figure out what the charge carriers were. It's such a simple, elegant experiment. If the voltage is positive left to right, then it was positive charges moving through the wire. If the voltage is negative left to right, then it's negative particles moving through the wire. This is how it was proven that the charge carriers in a wire were negative charges and not positive charges. And it's called the Hall effect. Nowadays, the Hall effect is used for all sorts of things. Because this effect is well understood, the Hall effect has been used in applications of other circuitry. But this is a simple, elegant experiment that was able to very well prove the motion of the charged particles through the wire.